Hello everyone, welcome to this course on nonlinear system analysis. This is the introductory lecture on the course. So, in this lecture we will look upon examples of nonlinear systems drawn from various disciplines such as electrical engineering, chemical process, biological systems, mechanical systems and so on. So, what we are going to see is first we will look at the linear system, right. We all know that a linear system is one which obeys the principle of superposition and homogeneity. Now, what is the advantage if you have the linear system? Of course, in nature no system is linear, everything is nonlinear, but suppose for our convenience let us say that you are given a linear system. And what are the advantages of using a linear system? Now, as we know that all systems in nature are nonlinear, so we will have to understand how to model nonlinear systems. That is the first step. Of course, the course is not about modeling the systems. We will take models from existing models from system. But for explanation, I will to get a feel of modeling, I will take the example of a simple pendulum system and explain its modeling. So, today we will see how to so as I said, first we will see the advantages of linear systems, then what is the notion of linearization, right, and why linearization is not a good tool to analyze a nonlinear system. Then we will see one particular example of a mechanical system, that is a pendulum system. We will derive its model. Then we will write down the state space representation of the system. Then once we have written the state space representation, then we will put it in some standard form. And then we will identify what is known as the equilibrium points and then the operating point of the system. So, this will be helpful for us when we want later on to do linearization about an equilibrium point and operating point. Just go through the linear system theory that we are already familiar. So, we have a system with m inputs and p outputs. So, we denote the inputs by u and the outputs by y. Right, and we say the system is linear if it satisfies homogeneity and superposition principle. That is, if I scale the input, right, say alpha u1 and beta u2, I scale it and then add it up, right, I get a output which is what you would have got individually if you had applied u1 or u2 and you would have scaled it. So, let us see what are the advantages of using a linear system. Okay. The first advantage is one can scale up the solutions to get new solutions, right. So, if you have two solutions, you add up and you get a new solution, and if you know the response of the system to existing set of inputs, we call it as a basis set of inputs, then you can generate the solution to any other set of input by a linear combination of the responses to these basis inputs, right. For example, if you know the response to a step input, then you know the response to a impulse input by just differentiating the output, right. And one can also show that the set of solutions of a linear system forms a vector space, right. So, a vector space has a structure when you define the notion of the so called addition and the so called scalar, the so called vector addition and the so called scalar multiplication, right. So, and if one can show that the linear system forms a vector space, and then we can use all the tools of linear algebra to do further analysis, right. The nice thing about one of the nice things about linear system is that one need not worry about the existence and uniqueness of the solutions. So, given a differential equation in general, nothing can be said about its existence and uniqueness if it is a nonlinear system, right. So, of course, you need to put some conditions on the right hand side of the differential equation. For example, if the right hand side of the differential equation is locally Lipschitz, then one is ensured of existence and uniqueness. But a linear system satisfies all those necessary the sufficient conditions for the existence and uniqueness. So, one need not bother about these two properties, that is existence and uniqueness. So, for all our purposes we can assume in fact the solution exists and is unique. And we have also studied the linear systems from a transfer function point of view. So, characterized by pose and zeros. So, a linear system is completely characterized by pose and zeros. Now, since linearization is a very powerful tool, because once you linearize, you have a linear system and it is a well studied notion, you know how to solve a linear system. So, the first step typically would be to linearize the system, to linearize a nonlinear system about some point. In fact, we will let us see about what are the kinds of points that we are interested where we would like to linearize, right. Now, but the problem also there is a problem associated with linearization, as you can see in these three examples, that I have a nonlinear system and I have linearized it about the origin. So, the linearized system is given by this line, the line segment, the blue line segment, right. So, in all the three examples, even though the nonlinear systems are quite different, the linearization throws up the same behavior, right. So, this is what is lost when you do linearization. So, it kills the nonlinear behavior, and the only thing you can comment is the local behavior, whereas one loses the global picture when one does the linearization. So, let us go back go to a simple mechanical system, the pendulum, the simple pendulum. So, the simple pendulum consists of a massless rod, right, with the length L, and then there is a the mass is assumed to be a point mass, right, with mass m here, okay, and the pendulum makes an angle theta with the vertical, right, and the whole thing can move under the influence of gravity. Now, we will assume that there is a torque that can be applied at this joint, right. Of course, we can talk about unforced pendulum or a forced pendulum. So, we will talk about a forced pendulum. Think of a motor which actuates this pendulum, right, and we will also assume that the pendulum is free to move in the vertical plane. It can make complete rotations in this plane, right. So, what are we going to study with this system, right. So, we have a simple pendulum as a mechanical system. So, for the first thing is we will derive the equations of motions, So, to do that, note that this system is a 1 degree of freedom system. That means, to specify the position of the any point of this pendulum, I just require one variable, in this case theta, and that is why the system has 1 degree of freedom, right. For example, one can think of a 2-link manipulator, right. So, something of this form. So, I require one angle here theta 1 and the other angle may be with respect to the first one theta 2. So, to specify say the location of this point, right, I require a minimum number of 2 variables to describe the pose of the system. So, this system has 2 degree of freedom. So, let us not go too much into the degree of freedom, right, but we now understand at least what is meant by a 1 degree of freedom system or a 2 degree of freedom system. Now, there are various ways to derive the equations of motion, and we will use what is known as the Euler-Lagrange equation. Okay. So, first we identify what is the degree of freedom. So, the theta is the degree of freedom here, I mean theta captures the parameterizes the degree of freedom here. So, the angular position here is the theta and the angular velocity is theta dot. Note that this theta does not belong to the real line. In fact, theta belongs to what is known as a unit circle. And what is this unit circle? It is a set of all points in R2 such that x square plus y square is equal to 1, right, all the points on the unit circle, because this is because we identify the 0 angle with 2 pi, right. So, 2 pi and 0 are same, whereas if you were to represent it on the real line, the 0 and 2 pi are different points, right. So, the space in which the angle evolves is S1. So, we call this as unit circle. So, let us write down the Euler-Lagrange equation for this. So, the Euler-Lagrange equation is given by d by dt of dou L by dou theta dot minus dou L by dou theta is equal to all the external forces acting on the joint, right. So, what are the external forces acting on the joint? There is only one joint here, this is the joint, right. So, let us call it as O, and what is the external forces? We will assume that there are no frictional forces. So, the only external forces is the torque applied to the joint, right. So, we will assume that this is a revolute joint. So, there is a torque applied to the, if there was no torque, then we will set this to 0, right. But because we want to model a control system, let us bring in the torque here, right. Now, what is the L in this? L is known as the Lagrangian of the system. And how is it defined? L is defined as kinetic energy minus the potential energy. So, what is the kinetic energy here in this case? So, the kinetic energy is half ml square, because we have assumed to be point mass, into theta dot square, right. So, ml square is the inertia of the point mass, right. So, kinetic energy is half I the velocity square minus, we will take the potential energy as mgl 1 minus cosine theta, right. Well, why did we take this? We took this because at theta equal to 0 we have 0 potential energy, and at theta equal to pi we have the maximum potential energy, which is equal to 2 mgl, right. So, one can always add a constant to the potential energy and it will not change the equations of motion. So, you can reset your 0 potential line the way you want, right. But in our case we have taken the downward position as the 0 potential line, 0 potential reference, and the pendulum at the upward as the maximum potential reference. So, now we have constructed the Lagrangian, right. So, the Lagrangian is a function of theta and theta dot, right. So, let us plug this into 1, right. So, what do we get? So, we have d by dt of dou L by dou theta dot, right. So, there is no theta dot in the contributed by the potential energy, whereas the kinetic energy contributes theta dot. So, you have ml square theta dot, right, minus dou by dou theta of the Lagrangian, right. So, there is no theta here, there is a theta here, right. So, there is a, one has to be careful about the signs, there are too many minus signs. So, minus minus plus, right, and the derivative of the cosine will yield one more minus sign, right. So, that will be minus sin theta equal to the torque. So, we get left hand side ml square theta dot plus, sorry, this is, we already took the derivative with respect to theta. So, we have mgl sin theta equal to tau. Right. So, this is a second order time invariant ordinary differential equation. So, the course is all about studying the analysis of an ordinary time invariant ordinary differential equation. It could be second order or third order, that does not matter, but what we are going to restrict is to time invariant and ordinary differential equation, right. Well, now we have the equations of motion of the simple pendulum, right. So, what do we do with this? Well, as control systems, we will try to put it in state space formulation, right. So, the next step is state space formulation. So, state space formulation is not just restricted to linear system, one can write the state space even for a nonlinear system. So, we have to choose states for this system. So, how many states? There will be 2 states because we have a second order system, right. So, we have x1 and x2. So, typically for a mechanical system, choosing the states is a very easy task, because what all that one has to do is to identify the positions and velocities, right. So, the set of positions along with their velocities will form the complete state space. So, here we have the position as theta and the velocity as theta dot, right. Of course, one can take position and momenta also, but again the momenta is related to angular velocity. So, it's a choice that we made, that we took the angle and the angular velocity as the states of the system, right. For example, if you had a mechanical system with only linear motion, then you would have taken position and the linear velocities as the states, right. And again, if you have a double pendulum, then you would have taken the states as x1 as theta 1, x2 as theta 2, x3 as theta 1 dot, x4 as theta 2 dot, right, the positions and the velocities, right. So, having chosen the states, let us write down the state space for the simple pendulum system that we have derived, right. So, I have x1. So, let us rewrite this equation, let me call this as equation 2, right, rewrite 2. So, I can solve for theta dot as minus g by L sin theta plus tau by ml square, right. I just divide it throughout by ml square. Now, the usual way that we do, we take the derivative of x1. So, x1 is theta dot and theta dot is nothing but x2 and x2 dot is nothing but theta double dot will come from this equation. So, it will be minus g by L sin of x1 plus tau by ml square. We will, for notational convenience, we will simply write this as u, where u is tau by ml square. I have just redefined the variable as u, because in controls u is identified with with the control input. Okay. So, again let us write down the system x1 dot as in a vector notation is equal to x2 minus g by L sin of x1 plus 0 1 times u. Note that I have rewritten the state space in a little special form, and what is the speciality of this structure? Well, let me name it and then we will see what is the speciality. So, I will call this vector as f of x and this vector as g of x, right. So, and the left hand side I will call it as x dot. So, I have called this vector as f of x, this vector as g of x. So, if you see, I have written the pendulum system as in the state space representation, but I have given us some structure to it and I have called it as x dot is f of x plus g of x u, right. So, note that f is a mapping from R2 to R2, it takes x1 and x2 and throws up a vector, right. In this case the vector is the vector of this x2 and minus g by L sin x1, and g also is a mapping from R2 to R2, right, because it takes two elements and gives you a vector in R2. Well, if you notice that f, the vector f in control, the vector f is called drift vector field. And the vector g is called, it is associated with the control, right. Note that the way I have split up the vectors is I have collected all terms which are not associated with the control, right, and I have collected all other terms associated with the control u, right. So, g is called control vector field. Now, the nomenclature for g is quite obvious, it is called control vector field because g is associated with the control, right. F is called drift vector because for the reason that in the absence of control input, right, the system, so if u were to be 0, then the system evolves as x dot is equal to f of x. So, how the x based on an initial condition x0 drifts is entirely determined by the vector f, the vector field f of x, right. The control input plays no role because you have set control to 0, right, and that is the reason f is called the drift vector field, right. So, equation 3 is called affine in control nonlinear system. So, in general f has components which are nonlinear, and so also with g. In this particular example of the simple pendulum, g is a constant vector field, it so happens that, but in general it may not hold, right. So, both f and g are nonlinear functions of x. The only difference between these two vector fields is one of them is associated with the control, the other is not associated with the control, right. So, we call the one which is associated with the control as the control vector field, and the one with not associated with control is called the drift vector field. Most nonlinear systems can be expressed in this form, right. So, I make no claim that all nonlinear systems can be put in this form, but most of the nonlinear systems can be cast in this form, right. What is this form? Affine in control nonlinear system. So, we have a state space representation for a nonlinear system, right. In particular, we took the simple pendulum, but one can, as I said, write it for many of the mechanical systems, chemical processes or biological systems or electrical systems and so on, right. So, what do we do next, right. So, let us find out let us define what is meant by equilibrium points. So, let us see what is meant by equilibrium points, equilibrium point or equilibrium points or continuum of equilibria and so on, right. Now, in this state space representation that we have, x dot is equal to f of x plus g of x u, right. So, set u equal to 0, there is no control, and second step, analyze, right, or let x dot be identically equal to 0. Identically equal to 0 means x dot is equal to 0 for all t greater than or equal to 0, right. So, what do we get? This equation reduces to, already we have numbered it, whatever it is. So, reduces to f of x equal to 0. So, f is a nonlinear function of x, right. So, solve for x from this nonlinear algebraic equation, right. So, here what we have is a nonlinear algebraic equation, right. So, the x, it may be unique x, it may be unique and isolated, or it could be multiple valued, right, or it could be a continuum. We will see that little later. So, this x, right. So, let us collect all those x which satisfies this algebraic equation f of x equal to 0. So, let me call that set as E. So, it is all x in, well, we have taken a general system. So, let me take here x as belonging to R n. We will take a single input R. So, the set of points in R n such that f of x equal to 0, right, is called the equilibrium set. So, what does it mean? That means there is no control input and the system. So, what are those states at which the system can identify, in the absence of any control input, the system can stay identically at that position, right, for all time t. So, let us see what these equilibrium points mean for the simple pendulum, right. Of course, from the physics of the system, we already have some notion of equilibrium points. We know that we identify the equilibrium position of the pendulum as there are two equilibrium positions, the lower and the upper equilibrium positions, right. So, we know a little bit from the physics, but let us see with our definition of equilibrium points, do we get the same points, right. So, for the pendulum system, so we had the vector field x2. So, f of x for the pendulum, simple pendulum, so we had x2 and minus g by L sin of x1 is equal to 0, right, because this is the drift vector field. So, if you solve this, it implies x2 equal to 0 that means the velocity has to be identically equal to 0, right, and sine of x1 equal to 0 implies x1 can be 0 or pi. We take 0 and pi because we identify all the solutions in the on the unit circle, right. We do not count the multiplicities of this solution. So, for the simple pendulum, the equilibrium points are all x in R2 such that, so you have 0 and 0, we have to take the ordered pair, right. First comes x1, second the x2. So, 0 and 0 is one equilibrium point and the other one is pi and 0, right. So, the equilibrium points for the simple pendulum are, there are two equilibrium points, they are isolated in the sense that in the vicinity of this equilibrium point there is no other equilibrium point, right, in a small neighborhood of that. That means, you can always find a small open set around this equilibrium point such that there is no other equilibrium point, right. So, these two are isolated equilibrium points and there are, so we have two equilibrium points which is in tune with the physics of the system that we already know from the physics of the system that the pendulum has two equilibrium points, right, and we exactly got those 2 points by our definition of equilibrium points. So, to recap, we model the system in a state space representation, we put it in a standard form which is called the control in affine in control nonlinear system, right, and then we, once the system is in this standard form, right, we know how to write the equilibrium points of the system or how to solve for the equilibrium points, right. Having identified equilibrium points, we will also need to understand what is meant by operating point. Well, so earlier we talked about equilibrium points when there was no control. Now, let us bring in the control, let us apply a torque to the pendulum. Suppose we were to hold the pendulum in certain angle not equal to 0 or pi, that means other than the equilibrium points. So, you want to say keep the pendulum in this position, right. So, obviously, we have to apply a control to compensate for the gravity, right. So, this point, this position is known as the operating point. So, the notion of operating point comes in various systems. For example, in power system we will talk the operating point is frequency, some say rated, in India we have the rated frequency as 50 hertz, the rated voltage for the consumer is 230 volts. So, that becomes the operating point, right. So, we want to, why are we interested in these points? Well, we would like to do some kind of linearization about that point and infer the system, we want to do local analysis of the system about that point, right. So, it is imperative that we first understand and extract what are the equilibrium points and what are the operating point, right. So, again let us go back to our pendulum system. So, we had x dot is equal to f of x plus g of x u. So, assume that I want to keep the pendulum at some theta star, right, where theta star is not equal to 0 and pi, that means I am excluding the sorry, this is star not theta dot, theta star I want to exclude the equilibrium points, okay. So, and I want to maintain the pendulum at this position. So, theta dot is 0, identically equal to 0. So, obviously, I will have to apply some tau star, right, or in our language we have replaced tau by u. So, let us call it as u star. So, what is, how do we get this u star? So, the goal is to find this operating point, right. So, already in the sense the operating point is already fixed, somebody has given us this theta star. So, what should be the u star, right. So, the operating point is characterized by both the position and the control, these two will completely specify what is the operating point. So, let us go back to this equation, our pendulum standard equation. So, my x dot has to be 0 because I want to hold the pendulum at that point, right. That means, my theta dot has to be 0, identically equal to 0, that means theta double dot also has to be identically equal to 0, right. So, x dot is 0 and then we have f of x star, because now the system is at some operating point, let us call it as x star, plus g of x star to u star equal to 0. So, what does this boil down to for the pendulum? So, you had x 2 star, right, plus g had 0 and 1. So, there is 0 here. So, that tells us that the velocity has to be 0, and the second term, second component is minus g by L sine of x 1 star. X 1 star is nothing but theta star, right, plus u star equal to 0. So, which implies, I think it has to be, yeah, this is fine. So, u star is nothing but g by L sine of x 1 star. So, this is precisely the effort required to hold the pendulum at an angle theta star, right. So, this torque compensates for the gravity. So, unlike an equilibrium point where u is 0, in an operating point u is not 0, there is some control that has to be applied to keep the position, keep the system in that position, right. So, the operating point is given by theta star, right, and g by L sine of x 1 star, or I can replace it by x 1. So, now we know how to find an equilibrium point and also the notion of operating point, right. So, then final step in this analysis is how to do the linearization, right. So, that will be the topic of our next lecture. Thank you.